In the preceding video, I began to explain the connection between probability distributions and statistics. In this video, I'm going to introduce to you, I'm just going to get you a taste of what the main branches of statistics are. We've got Bayesian statistics and Frequentist statistics, and so I'll talk a bit about their history and how they incorporate probability. So Bayesian statistics can incorporate prior knowledge from, for example, experimental results or beliefs that you have. And this is really how lay people, how ordinary people, how people who aren't trained statisticians think about probabilities. Their thinking is in line with Bayesian thinking. So if you say something like, there's an 80% chance it'll rain today, that is how the Bayesian philosophy thinks about statistics as well. So the field is named after the English philosopher and minister Thomas Bayes. He devised a particular case of what's today called Bayes' theorem in 1763. And you might think that I have him pictured here, but I don't, because there aren't any known pictures, or paintings, I guess, of Thomas Bayes. So even his notes weren't published by him when he was alive. They were published post-mortem by someone named Richard Price. Now, the person who's pictured here is a French polymath named Pierre-Simon Laplace. So in the late 18th century, early 19th century, he refined Bayesian statistics beyond the single theorem that Thomas Bayes identified in 1763. So he expanded Bayesian statistics to probability and statistical problems. Some drawbacks of this Bayesian approach, which is quite old, as you can see, is that beliefs, incorporating beliefs into some supposedly objective process like statistics, is icky to some people. And there's reasons why this isn't a big concern to me. We'll talk about that more later on in a lesson on Bayesian statistics, much later in these live lessons. Another drawback of Bayesian statistics is that it's generally computationally expensive. So for many centuries, there weren't a large number of problems that you could apply it to because we didn't even have computers. Okay, so other than Bayesian statistics, the other big school of statisticians are the frequentists. So frequentists focus on supposedly objective probabilities. And I put that in scare quotes here on purpose because there's lots of situations where those probabilities aren't really objective anyway. I'll talk about that in a second again. So frequentist statisticians think about statistics in an unintuitive kind of way that requires training to really start thinking this way. So where the Bayesian or the layperson might say, there is an 80% chance it'll rain today, the way that a frequentist statistician would phrase that sentence is, on 100 days exactly like today, it would rain on 80 of them. So what makes frequentist statistics still not really objective is that it has an arbitrary threshold where we say if the event that you observe had a less than 5% chance of occurring by chance, then that is a statistically meaningful observation. So going back to our probability distribution of a fair coin, we found that there was a 3.1% chance that we would flip 5 heads in a row with a coin. So if we flip 5 heads in a row with this coin that my friend gave me, a frequentist statistician would conclude that this is not a fair coin because there was only a 3.1% chance that I would get 5 heads by chance alone. And because that 3.1% number is lower than 5%, that's what this arbitrary threshold is all about. So Frequentist statistics was discussed as early as 1837 by Siméon Denis Poisson, and it was expanded in the 19th century by many people, including John Stuart Mill, John Venn, and George Boole. However, the modern frequentist statistics that we work with today, including in these live lessons, was largely developed in the 20th century by Sir R.A. Fisher, who's pictured here in the orange surrounding, and Carl Pearson, who declined being knighted as a Sir, shown here in the green portrait. So these two gentlemen are responsible for a lot of the modern statistical techniques that we have today, and we will focus on that in the second half of these live lessons when we dive deep into statistics. So if you happen to study statistics at university, say, odds are that you learned only about frequentist statistics, and Bayesian statistics might not have even been mentioned. So frequentist stats was the only statistical approach taught in the 20th century, really. And even largely in the 21st century, that still holds true. So an advantage of frequentist stats relative to Bayesian stats is that it's generally computationally inexpensive. But the drawbacks are that it's not designed for large feature sets, so it doesn't handle having a large number of inputs into a model very nicely. And that 5% threshold that we talked about already is far too high for large sample sizes. So in the modern world where we have tons and tons of data for a lot of problems, we end up having supposedly statistically significant findings that are below that 5% threshold, all the time. If you have a data set of 1 million data points, almost every relationship that you find in that data is going to be supposedly statistically significant at that 5% threshold. And so this threshold was designed at a time when in your experiments you'd often have 8 observations or 16 observations or something like that, not thousands or millions of observations like we have today in a lot of cases. And the final big drawback from my perspective with frequentist statistics is that prior probabilities are ignored. So while Bayesian statistics has those prior probabilities, and some people find them icky because we ignore them, in a lot of cases, those prior probabilities are valuable. They could be based on some knowledge that we have about the real world, so that the experiment we're conducting and the results we're analyzing aren't standing alone in their own supposed separate world like frequentist statistics envisions. So these prior probabilities can have a lot of value. We'll talk about that much more later on in these live lessons. All right, so on these couple of slides about Bayesian and frequentist statistics, hopefully you're starting to get the sense of how important probability theory is in any kind of statistics and any kind of inferences that we make using statistical models. Up next, we'll talk about the relationship of probability theory to machine learning specifically.